This is a lecture series under the course of stochastic modeling and the theory of queues. We were looking at the renewal theory under the broad category of stochastic processes. After looking at the defining nature of the renewal processes and the way of characterizing the renewal processes, we are going to look at a very important concept called as the renewal function. Let us consider a renewal process n of t greater than or equal to 0. This is a counting process with a discrete state, continuous time, and the time between the occurrence of two events, which we will call it as renewals, have a general distribution with finite expectation. So E of n of t is defined to be the x, if x1, x2, x3 denote the time interval between successive events that occur, and they have a general distribution with a finite mean, which we will call it as x bar. At any given time t, n of t denotes the number of renewals that has occurred till that time. And if we take the expectation of that, which is denoted as E of n of t, that will give you the expected number of renewals that would have occurred in the time duration 0 to t. We call this as the renewal function. We will give a notation m of t to stand for the renewal function defined at a time t. It is nothing but the expectation of n of t. So we have already seen that probability that n of t equal to n, probability that number of renewals that would have taken until time t, starting from a time t is equal to 0 to be equal to n, that can be arrived at using the formula p n of t equal to n is equal to f sn of t minus f sn plus 1 of t. We derived this in the last lecture. Sn is the time for the occurrence of the nth renewal, and f sn of t is the cumulative distribution function for this random variable Sn. Similarly, for Sn plus 1 is the time for occurrence of the n plus 1th renewal. We found that if you subtract f Sn plus 1 of t from f Sn of t, we get probability that n of t equal to n. Although this is a useful formula, it's not very convenient way of arriving at, and it may have too much of information. Rather, a quantity that would be of interest to us is just the renewal function. For example, the renewal function may give you an idea of how many renewals will take place in a time t. We can arrive at this renewal function using some formulation as given here. Let us look at x, which is the a discrete random variable, any discrete random variable. We can try to arrive at a property which is generic in nature and which can be applied to this equation to simplify this probability n of t equal to n. Let x be a discrete random variable which is non-negative. Then its expectation E of x is given by sigma n equal to 0 to infinity n into probability x equal to n. But this n itself can be written as sigma k is equal to 1 to n probability x equal to n. See, look at this summation. In this summation, the index is k, but within this summation, index doesn't occur, which means that we are simply adding this quantity n times. K is equal to 1, 2, 3 to n. So the effect of this summation is simply to multiply this by n. That is what is given here. So this is a dummy summation. We simply add this n times. That is what is n into probability x equal to n. Now look at this double summation. One of the summation index, there are two index n and k. N varies from 0 to infinity while k varies from 1 to n. So instead of that, what we can do is we can let n varies from 0 to infinity and another variable ranging from n to infinity. So when n is equal to 0, then here k will have no range. When n is equal to 10, k will vary from 1 to 10. So as n increases, the range of k also increases. When n becomes infinity, range of k will also become infinity. So it starts with no range and goes all the way to infinite range. The other way is to let k varying from n to infinity. When n is equal to 0, we have 0 to infinity, and when n becomes infinity, we have no range for k. So there are two ways of actually varying the range of these two variables indexes. Both are equivalent, and therefore we can, instead of letting k is equal to 1 to n, we can let n to infinity. And we know what this one is. This can be written as probability that x is greater than or equal to n. And so expectation of n is sigma n is equal to 1 to infinity probability x greater than or equal to n. Probability x greater than or equal to n is 1 minus probability x less than n. Probability that x is less than n is the CDF function of x, that is fx of n evaluated at n, and therefore probability x greater than s is the CCDF, which can be denoted as f bar x of n. Therefore expectation of s can be written as sigma n is equal to 1 to infinity f bar x of n. So this is a very alternate way of writing it. So we can use this probability that expectation of n of t, which is if you want, sigma n equal to 1 to infinity probability n of t is greater than or equal to n, can be written like this one. And therefore we know that n of t greater than or equal to n is equivalent to Sn being less than or equal to n. So we can write this like in this manner. So expectation of n of t, which is the renewal function, can be written as sigma n is equal to 1 to infinity probability Sn being less than or equal to n. And what is this? This is the CDF of Sn. So we have got a useful formula for the renewal function. It is nothing but sigma n is equal to 1 to infinity f Sn of t. So this can be used to get renewal function when the CDF of Sn of t has got a simpler notation, and you have to do a summation of this series. So m of t, basically the renewal function, may be useful under various scenarios. For example, if you have a light bulb that we have to put into use in a factory, and so we use a bulb, and as soon as it gets fused, we replace it by another bulb, and so on. So every time we replace an identical bulb, the lifetime of the bulb gets renewed, and therefore it is a renewal process. What you might be interested is in 1 year, what is the expected number of bulbs that we have to put into use. Therefore, if you know the renewal function, given the lifetime of the bulb, given the lifetime of the bulb x, you would be able to characterize Sn of t, that is the distribution for the renewal of the 6th bulb, 7th bulb, and so on. Once you have all these things, and if you add it up, you will get the renewal function. And if you can evaluate it at t is equal to 1 year, you will know what is the expected number of bulbs you have to put into use in 1 year. So that is the advantage of dealing with the renewal function. Now let us try to derive the renewal function using an alternate formalism. Let us derive this in a usual alternate manner. We know that x1, x2, x3 denote the time for the occurrence of the first renewal. x2 is the time difference between the second and the first renewal. x3 between the third and the second renewal, and so on. And which can be used to get Sn for any arbitrary n, and that can in turn be used to get m of t. But now let we derive or represent the renewal function m of t, which is the expectation of n of t, by conditioning it on the value x1 will take. Okay. If you put this condition, is there a way of finding expectation of n of t? Then we can uncondition on x1, that is letting x1 to take all possible values of x, and make use of it to derive at expectation of n of t, or the renewal function. Okay. So supposing the first renewal, let us look at this figure. We are interested in finding m of t at time t, that is the expected number of renewals that would happen by the time t. Let the first renewal take place at a time x less than t. Okay. So x1, the time for the renewal, first renewal to take place, is equal as a realization of small x. Then we have a remaining time interval of t minus x, in which the rest of the renewals should occur. If you know the expected number of renewals that will take place in t minus x, and add with that the first renewal that would have occurred at x, we will know the expected number of renewals that will take place in 0 to t. So the expected number of renewals in 0 to t is 1 plus the expected number of renewals in the interval t minus x, if x is the time it takes for the first renewal to take place. So that is the basic idea we are going to use. So expectation of n of t given x1 is equal to x is 1 plus the expectation of n of t minus x given x1 is equal to x. But here x itself can range from 0 to infinity. So we will make use of that. Of course, if x is more than t, then no renewal will take place here, but still x can take any possible values. So we will do this one. But if x is greater than t, then 0 renewals would have occurred within 0 to t. So that range, if you t to infinity, if you try to include it, that will contribution is 0. So we can stick to 0 to t. So expectation of n of t can be written as expectation of n of t given x1 is equal to x into this weighted by the density function evaluated at x, small x, and integrated over the range 0 to t. So we uncondition it by letting x1 is equal to x, and then uncondition it by multiplying the density function at x, small x, and integrating it over the valid range. And we know that this can be written as 1 plus expectation of n of t minus x given x1 is equal to x, and so on. Now we'll know that the first renewal has taken place at the time x starting from 0, and this we are asking about the expected number of renewals in the non-overlapping time interval t to x to t. From the nature of the independent increment nature of the process, the expected number of renewals in this time interval is not dependent upon the value taken by x1. Therefore, we can drop this. So it will be simply expectation of n of t minus x. So the integral becomes integral 0 to t 1 plus expectation of n of t minus x into fx of x dx. Now let us substitute in place of expectation of n of t is the renewal function. So this would be the renewal function at t, which is denoted as m of t, and this would be 1 plus m of t minus x. So m is a function of the interval. So expectation of n of t minus x is m of t minus x into fx of x dx. So we have got a integral equation for m of t. That is the most important thing. So in a recursive manner, we have defined m of t in terms of m of t using an integral equation. We can solve it and get m of t. To do that, what we will do is we will just write it, split it into two parts. Integral 0 to t fx of x dx by multiplying this with 1, and integral 0 to t m of t minus x fx of x dx. And we know that this is nothing but the CDF of x, which is capital fx of x, fx at t. This is CDF at the value t, plus 0 to t m of t minus x fx of x dx. So m of t can be written as fx of t plus 0 to t m of t minus x fx of x dx. So this is a formula, this is a one that we can make use of it to solve for m of t. Let us take a simple example and get the renewal function for that particular example. For that, let us take x, the general distribution governing the time between duration between successive renewals to be uniformly distributed between 0 to 1. So x1, x2, x3 are all IID uniformly distributed random variables taking values between 0 to n. X is uniform between 0 to 1. So in this case, what will be the m of t? So now if you recall the properties of the uniform 0, 1 random variable, its density function fx of x is 1 for x lying between 0 and 1 and 0 otherwise. This would be the density function. Height is 1 so that it is normalized, and the CDF is a linearly increasing function starting from 0 at x equal to 0 going up to 1 at x equal to 1. So fx of x is x between 0 to 1 and it is 1 beyond x. It will be 0 for less than x. Of course, that is to be mentioned. So let us make use of this and substitute it here to get a formula for m of t. So here it becomes at the time t, if you put it will be just t, and here this will become 1. So we get m of t equal to simply t plus integral 0 to t m of t minus x dx. Okay, so this is what you would get. So how do we solve it? We use some simple trick. We will differentiate it to convert it into a differential equation rather than an integral equation. Again, for that we will change the variables. Let us define a variable y which is t minus x. Okay, we will change it. We want to get rid of this variable. Instead we will let t minus x is equal to y. Therefore minus dx is equal to dy. So here if you look at it, m of t equal to t plus. So when x is equal to 0, y is equal to t. So the lower limit becomes t. When x equal to t, t minus t equal to y is equal to 0. The upper limit becomes 0. So the limits changes from t to 0, but dx becomes minus dy, and therefore we can let it to be plus dy and change the limits, upper and lower limit, and retain it as 0 to t. So if we change the limit, this becomes t, this becomes 0, and dx becomes minus dy. You have this one. So we can change the limit and change this minus to plus. So we have got an equation like this. Now we will let we will differentiate this. We will get m dash of t is equal to 1 plus m of t. T becomes 1. If you differentiate with respect to t, it becomes the integrand evaluated at the upper limit, because the lower limit is 0. Incidentally, m of 0 is also 0. Therefore it simply becomes m of y evaluated at t, that is m of t. So this is the differential equation we get. To solve it, we will define another function h of t, which is 1 plus m of t, and therefore h dash of t is also equal to h of t. So with this transformation we get h dash of t is equal to h of t, and therefore it will be dh of t by h of t is equal to dt, which on integrating we will get natural logarithm ln of h of t is equal to t, and therefore h of t will be simply e power of t plus c. To find this integration constant, we can evaluate this at t is equal to 0. Before that we will come back to m of t. H of t is 1 plus m of t, so m of t, so in place if you put this 1 plus m of t and then take that 1 here, m of t is minus 1 plus e of t plus c. At t is equal to 0, m of t is the number of renewals in the interval 0 to 0, which has to be 0. So m of 0 is 0. 0 is equal to e power of 0 is 1. Minus 1 plus 1 becomes 0. So c becomes 0. Therefore m of t is nothing but e power of t minus 1. So we get a very useful formula that if you have a sum of renewals that takes place such that the time between two renewals is uniformly distributed with 0 to t, then the number of renewals that will happen in any given time t is simply given by e power of t minus 1. So that is a very useful formula that we can make use of. Then we will derive what happens to the renewal function when you consider very large intervals. First thing we can see is that the number of renewals that will happen over an interval of size infinite can be easily found out if you know the expectation of the inter-renewal times. Okay, if x bar is the expectation of the random variable x that govern the generic distribution between two renewals, and if you let mu to be equal to 1 over x bar, mu represents the rate at which the renewals occur, then this limit theorem tells that in the limit t tends to infinity, n of t by t approaches 1 over mu. So if you take a very long time interval, find the number of renewals that takes place in that interval and then divided by the time interval, we would get the number of renewals per unit time. That is equal to the rate at which renewals occur, which is 1 by mu. So this is what this theorem tells. We can find it out. Let us take any time t. Then we will look at Sn and Sn plus 1. We can easily see that t should lie between Sn n of t and Sn of t plus 1. S of n of t plus 1, not of n of t plus 1, n of t plus 1. See, what is n of t? The number of renewals that would take place in a time t. In this particular example, 3 renewals have taken place. So n of t will be 0 up to this point, it will be 1 in this point, 2 in this interval, and it becomes 3. It will remain 3 till this point and then jump to 4, 5 here and so on. So n of t is equal to 3, which means that before t 3 renewals would have occurred and 4th renewal should occur only after t. So t should lie between S of n of t and S of n of t plus 1. So this is an important relationship we have. So t lies between S of n of t and S of n of t plus 1. So it is always S of n of t plus 1. That is the most important one. So what we have here is that using this relation, we will divide this inequality by n of t. So S of n of t by n of t is equal to t divided by n of t, like this one. And let us take look at this first factor. What is S of n of t? Is the number of renewals, the time at which the renewal denoted as n of t will occur. So n of t renewals have taken place, and let x1, x2, x3 be their time between those renewals. So S of n of t is sigma I varying from 1 to n of t xi, where xi's are all realization of the generic distribution x divided by n of t. So this is the average. We can see that this is in the limit t tends to infinity, n of t tending to infinity. So this is the average of ensemble average of x. Okay. And therefore we can see that what is this? This is the time divided by the number. So that will converge to mu. Okay, n of t divided by, okay, so this is what we find that happens when n of t tends to infinity. So S of n of t by n of t tends to mu as t tends to infinity. Furthermore, if you look at this one, we can rewrite it as S of n of t plus 1 by n of t can be written as S of n of t plus 1 by n of t plus 1 into n of t plus 1 by n of t. We have divided and multiplied by n of t plus 1. And again in the limit t tends to infinity, this converges to mu, and this factor n of t plus 1 by n of t, as t tends to infinity, n of t tends to infinity, and this factor tends to 1. and both of them tends to mu, and therefore this factor will also tend to mu. So T by N of T tends to mu, so N of T by T tends to 1 over mu. So this is what we find. So that proves this limit theorem. So far we looked at the renewal function M of T and its usefulness through an example, and also looked at one very important limit theorem and what will happen to the number of renewals when the interval size is very large. Thank you.